Let's try it again. Click. Nope, no good. Okay, so I can't actually see the rest of this. I thought I could click on it and see, but it's not letting me do that. Okay, so I've gone through the cross entropy math. I've told you how to calculate the derivative of the vector. It's actually very simple. It's actually, again, just partial derivatives. So they're all a bunch of one-dimensional problems. Just you're just doing them simultaneously on all of the fronts. Okay. Sometimes the vector notation looks really, really clean, and when you actually try to work it out, you'll see that it actually makes sense. Okay, but you can think, okay, there's this huge vector. How do I do it? It's just basically going through each of the components. So if you have one component and they're independent of each other, you can make that generalization for all components, and you can come up with a nice vectorized form for the math. Okay, so I hope over the course of your linear algebra class, you had some practice with that. If you didn't, well, this is the time, right? Still trying to get enough practice on it. Okay, can I explain the definition of gamma? Okay, so let's try to find gamma. I think that was in the earlier part of the, I think this was on the proof, right? Okay, here, right? Is this the one that you're talking about? Okay, so basically what we're looking at in the perceptron learning algorithm, when we're trying to do the convergence, let me just try to outline what we're trying to do here, okay? Okay, the basic idea is that we want to be able to come up with a proof for convergence, right? So what we're doing here is thinking of the iterations, right? So these are the iterations of the perceptron learning algorithm, right? And what we want to do is find a fixed point, right? We want to say that at some point in the future, okay, starting out with some simple hyperplane, like a hyperplane that's just flat and going through the origin, okay, having all weights 0, okay, I'm going to emerge victorious by finding a linear separating hyperplane, okay? And so what I want to do is define this K max, the maximum number of iterations that is necessary for getting an answer, okay? And basically the line of argument has two parts, right? There is an upper linear bound for how much this vector is going to change from its initial value after a certain number of iteration, okay? And we're also going to see that the bottom, the lower bound, is actually growing quadratically. So at some point, these 2 points are going to intersect, okay? When they intersect, we know that is actually a maximum. It's not a very tight max, okay? In fact, you can probably do better than this through other proofs, but that's not the point. The point is just to say that because we can find this K max, okay, that means that it must converge, okay, if it's linearly separable. That's all we're saying, okay? So that's the idea of the perceptron learning algorithm convergence proof, okay? So as we said before, what we need to do is think of a particular notation. This notation here is the squared of the norm of whatever is inside. So this is the squared of the norm of the weight vector, right? That's being wiggled around. Okay, so hopefully you understand what that means. Okay, and so what we're going to do is not step through the whole thing. Okay, we're just stepping through parts of it. The one part that you really wanted to know about was about the gamma. So we're just going to skip to that. So in the lower quadratic bound part, right, we have this idea of this weight vector divided through by its norm, right? And this is basically the separating distance between the separating hyperplane that we have currently, okay, and an x, okay? So whatever the x is that we are trying to get is the particular instance that we're looking at, okay? So what we're doing here is defining this gamma, and this gamma is basically telling us the length, okay? The length of this line segment, okay? Which when in this particular lecture this week, we talked about it in the idea of an SVM, okay? And the SVM is really, really cool. If you get a chance to look at it in the pre-lecture this week, which I hope you do. I think you'll find it very intuitive, okay? But I'll just try to recap it a little bit here, okay? When we have a hyperplane, okay, to try to separate a set of points, you can see if I had these 2 points not in here, then somehow it's easier for me to set a hyperplane, right? Because I could set, you know, even something like this, or this, or this, and they would all be good, right? Because they separate the positive examples from the negative examples cleanly, okay? Now, on the other hand, let's imagine that I had additional X's and O's. Let's say I had an O here and an X here, okay? Suddenly, the problem is a lot harder, right? Because the set of hyperplanes that I can use to classify things properly have to fit somewhere between the space of these parts, right? If they don't go through here somehow, at least one of the examples will be wrong, right? Okay, so what we're going with here is to understand that this margin, this separation of space between the hyperplane and a misclassified example is actually telling us how difficult the problem is to find the classifier, okay, a good classifier, right? If I had the first example where I took away 2 of the X's, it's pretty easy. On the other hand, if I introduce this extra O and extra X here, it becomes a lot harder, okay? So depending on how close these 2 classes are from each other, given that they are still linearly separable, it tells us how much more difficult the problem is, okay? So the larger the margin, our gamma here, which is this norm, okay, that we're dividing through, the more difficult it's, the easier it's going to find to place that hyperplane, okay? So again, remember, PLA doesn't care which margin, which hyperplane we do. As long as we find one, either this one, or this one, or this one, it's all good because we have no misclassified examples. The iterations will stop and we're done, right? Okay, so that's the whole point. It's like when we have a smaller margin, it becomes more difficult. We have to get much more precise about exactly where that hyperplane goes, okay? So that's what we mean by this, right? So when we have smaller wiggle room, okay, a smaller case here, then we really don't have a lot of options to place our boundary, okay? All right, so when we have defined that, okay, and we have this idea of this norm, okay, that we are using, right? Then we can square both sides and use this Cauchy-Schwarz inequality, and we're not going to go over that, okay? That's just basically finding another bound that's more convenient for us to estimate, and then we're going to use that together to find a bound, this quadratic bound at the bottom, okay? So when we put the 2 bounds together, the ones from the top, okay, our upper bound and the lower bound, right? The lower bound is here. This is the right-hand side, right? This is the right-hand side. This is the lower bound, okay? And the upper bound is over here, okay? Then we can solve it, right? And when we solve it, then we can find that K, this is our maximum number of iterations, is basically some constant times this thing, right? Which is basically the size of our margin, okay? The margin squared, dividing through the norm of our weight vector, okay? So the important thing for you to understand is not so much the math, okay? It's just that when we have things, the separation is actually very tight, then it's going to just take exponentially more time to converge, right? That's the bottom line that, of the proof that I want you to take away from this, okay? Because this leads up exactly very nicely to our SVM lecture that we are talking about this week, and which is that when we try to place this hyperplane, okay, this nice hyperplane over here, we want to place it in such a way that is going to maximize the distance between the points, right? We said in the PLA, we might consider a line like that perfectly fine. Sure, it gets everything right, okay? But it's not a particularly good line because it doesn't maximize the margin, right? What we mean by this margin is this thing here, right? This length, okay? If I want to maximize this length, right, between any point to the hyperplane and still get everything right. Somehow I need to find the points that are defining where the hyperplane sits, right? So these 3 points might make up the points that help me define a straight line that's going to maximize this distance, right? So let's say all 3 of these are at right angle norms, okay, and they're all the same length. Then somehow this particular hyperplane is uniquely optimal for classification, okay? And that's what we're going to see in the SVM lecture this week. All right. Okay, so I think I've gone over the gamma, I've gone over the cross entropy, okay, and I've gone through pretty much most of the math in the post lecture, the parts that I think actually matter a lot. The proof we can try to step through as well if you'd like, but I think it's easier to do that through technical detail, probably in text, because I'm afraid I might get some of it wrong. Okay, so okay, what's the difference between combining the weights and the bias into one matrix theta and using 2 matrices W and B to represent them? Okay, so this is a good question. Okay, we have basically, okay, let me just move over here. All right, we have basically this X matrix, right? And for the purposes of doing certain types of computation, for example, for our SVM lecture, okay, we actually have to separate them into a set of weights, okay, our thetas, which are going to be responsible for our slope, and an intercept, okay, which is going to move us off of the origin. Okay, you can think of it as very simply, right? And when we have theta in one dimension, it's basically giving us the slope, okay, the slope of the line. It's our mx plus b, right? Okay, and the b is helping us move from this point off. So our hyperplane is allowed to sit somewhere else, all right? If we have a positive b, maybe it looks a little bit like that, okay? So this is basically representing the direction, right? The direction and the orientation of this hyperplane that we're positioning, okay? So it's important to get that right, but it's also important to be able to translate that particular hyperplane to a particular location, okay? Without that, we can't move it off of the origin, okay? And when we do this, this type of decomposition lets us maneuver certain properties better, okay? So we need to separate the offset, which is represented by B, okay, and the direction of the class hyperplane that is dictated by our W's or our theta, okay? When we have this, basically, again, in our data matrix, we have, let's say, x1 all the way to xn, and we have theta 1 through theta n, okay? And those are all fine, but we need an extra observation, okay? We're gonna insert an extra artificial observation called x0, okay, which is always going to be 1, okay? And I'm going to just have a theta 0 that's going to allow me to tune where my offset is, right? If the observation of x0 artificially is always 1, then whatever value I set for theta 0 is basically my intercept, right? It's my b. Okay, it allows me to move the hyperplane off of the origin and put it anywhere I want in space. Okay, so that is the importance of being able to represent something in, as a matrix as a set of direction coordinates as well as one for an offset. Okay, so I hope I answered that. I'm really sorry I can't click in. I have to go read the instruction manual. Okay, what's a noisy target? Okay, so let's go back to that. I think that was in the pre-lecture as it said on the slide. So let's go open that up. So you said it was on slide 39. Okay. Okay, here. Okay, so we have binary y, right? It's generated by a noisy target. Okay, so we don't know whether it's actually true or negative. It's maybe our observation is off. Okay, again, a noisy target has to deal with an idea that our y could be wrong. Okay, that instead of having a +1, it's actually a -1, or instead of a -1, it's actually a +1. Okay, again, the difference is between a noisy target and noisy data. Noisy data means some x value, okay, might be off. Okay, the SVM handles this case very well. Okay, the noisy target means our y value might be off. Okay, so if we're doing regression, then we have a real value that's off. If it's something like a categorical value, like a binary case, it means that it's been flipped around, right? So here, all we're saying is that we're going to interpret the probability of the y value as being the probability of a noisy target as well, okay? So if we think that it's very highly likely it's positive, okay, meaning our signal, our S, right, our S, which is our theta times x, is a very high number, then with high probability, it's going to be a +1, right? So it's not very likely to be noisy. But if our signal is approximately 0, okay, very close to 0, then we're less certain. Our probability is closer to 50%, and then the noisy target will factor in more. Okay, so that's what we mean here. Okay. Okay, can we go through how gradient descent is calculated? Sure. Okay, so let's go back there. All right. Okay, so we're looking for the direction. Okay, again, the direction doesn't have our bias. Okay, so when we talked about it earlier, we're saying we're just looking at the set of weights that are associated with the data points, right? The instances actual vector outputs, okay? And what we're doing is we're saying, well, we want to know which direction is going to minimize our training data loss, right? And we're going to do that by taking a look at where I currently am, okay? Where I could go next iteration, okay? And subtracting the difference. So this is sort of like Newton's approximation, right? So you're looking at the difference and deciding where to step, okay? All right. And so when we want to do this, we're saying, okay, we're going to take this guy and redecompose it into something like this. It's going to be the same thing as what we had before, but we're taking a step. We're taking a step with a certain step size. This is the red mu, and this nu, which is our direction, which looks like a V. Okay, so we're just taking these two components, multiplying each other. This one is a scalar, and this one is a direction. It's a vector, right? Okay, so when we do this decomposition, right, then what we can do is say, hey, well, this is not very important. This is a scalar, so I'm going to move it out. Okay, so I'm going to toss it on this side. Okay, and then I just have to deal with this whole part here, right? So I'm going to notice that when I do this, I can think of it as a linear approximation, something like this, okay, which is just the difference between the two values, okay, at x1 and x0. Here, we're not talking about the particular things up here. Sorry, this notation is a little messy. It's between the x1 and x0 at these 2 points, okay, in these 2 iterations when I step forward or not, okay, and then some higher order terms. So when we think about taking a step, okay, let's say the landscape is a little bit like this, and I have a gradient like that, okay, what I'm going to do is I'm going to take a step, okay, maybe this is my step length, okay, my nu, okay, and sorry, it should be the other way around, right? So let me draw that properly. Okay, and I have my v direction, or mu is pointing up this way. So I'm going to go in the opposite direction. I'm going to take a step like this. Okay, so I'm going to end up with these set of weights here. Okay, so this is an approximation. So this line here might be a third order or a higher order polynomial, but I'm approximating it with a linear case, right? So I'm going to be off by a little bit. You can see that I'm off by quite a bit here, right? This is the actual value, and I step down here. These higher order terms are squared values. I'm just going to leave them out, okay? So these higher order terms I factored in here, okay? But because I'm doing an approximation, I don't want the, even though I might want the actual direction, it may be too expensive to compute. So I'm just going to get rid of it. I'm just going to accept the fact that I'm going to get some error by doing a linear approximation, okay? Not a quadratic approximation. A quadratic approximation would have these squared terms, and I might actually get back to something close to this point instead of having this linear case, okay? So then I've got this formula here, and then I can just take the norm of it, right? And then I'm going to use a unit vector to scale things because I'm going to use this, okay, in order to get the actual step size rather than thinking about how big the step should be, okay? So I only want the direction, okay? So the direction is just going to be this, right? This is the negative of the gradient, and this is the direction of the gradient, okay? So hopefully that clears that part up a bit, okay? So all this slide is trying to tell you is that I'm using a linear approximation, right? Because basically when I came to this step in the middle, sorry, let me clean up the slide again. Okay, okay. When I came to this step in the middle, okay, I'm taking the Taylor approximation, which has all these nice things. I can decompose it out into many more terms, but I'm just going to discard it, okay? I'm just going to get rid of all these terms and just think, okay, this is the only thing that I care about. It's our linear approximation, and I'm going to turn it into this particular direction, okay? All right. Okay, so what else can we do? How can we use a linear classifier such as PLA to classify more than two classes? Very good question. Okay, so when we want to do multi-class classification, there are a whole bunch of different techniques to use, okay? The simplest one that we can tell you about, which everyone does use, is what we call okay, I should be on the PowerPoint in order to do that, okay? So let me clear all this stuff. My Zoom hasn't died yet, so I'm actually impressed. This last week, I lost my tutorial section twice. That's really embarrassing. Okay, so when we do PLA and we want to do it for multi-classes, okay, generally what we're going to do is do something called one versus all. Okay, so if I have class 1, class 2, and class 3. Okay, let's just take the case of 3. Then what I'm going to do is I'm going to create 3 different PLA problems. Okay, so it's going to be 1 versus 2 plus 3, 2 versus 1 plus 3, and 3 versus 1 plus 2, which means I'm just going to take the 1 and treat it as a positive example, and take 2 and 3 and treat it as a negative example, okay? And I'm going to do that for all 3 of these problems, okay? So I've got 3 separate problems, and I can run PLA on all 3 of these, right? I'm going to run PLA on all 3 of these, and then find a way to break ties, right? So many cases it might say, you know, in the 1 versus 2, 3 case, and the 3 versus 1, 2 case, both of these will say maybe, okay, this particular instance X is a negative example, okay? And this particular instance X is also a negative example. Okay, well, now it froze. And let's hope it comes back, okay? Is also a negative example. And then, you know, from this, if I have it as a positive example here, I can get an output, okay? It's definitely class 2 is the winner, okay? When we're not that lucky and we have ties between all of these things, then we have to find some other voting mechanism to break ties. So we might say, if PLA is able to output a probability, meaning how close a particular instance is to the hyperplane, again, we can use some idea of, like, say, logistic regression to assign a probability to it. Okay, we haven't gone over that because we've only taught vanilla PLA. But we can do this for a lot of classifiers. We could try to get a confidence score out of it. And we already saw how that works for logistic regression, okay? So these confidence scores can be used to break ties when there's a classification tie, okay? So I hope that answers your question. Okay, there are a lot of such things, like say in the image classification model that we introduced, where you're taking a sum of all of the pixel differences. Again, could say the class that has the lowest pixel difference is the one that wins in that case. Okay. Okay, for collab questions, I think some of you need to remember how the matrix operations work. One of the problems that we keep on seeing students have is forgetting that the classification, that the dot product operator is sensitive to the order of operations, order of arguments. Okay, so you may have run into this problem where you call it something like NP dot. Okay, and you have two options here. You can call X theta or theta X. Okay, and these two are not equivalent. Okay, so you need to make sure you understand the order of the arguments because they mean different things. You're taking the axis of one of these and multiplying it against the other one. Okay, so if your axes are wrong, you're multiplying the wrong part of the vector. Okay, the height times the length, the row. Okay, then you may end up with an incorrect answer. Okay, in the logistic regression workbook that we did, there are some cases in which we had very simple test cases, okay, that should work no matter whether you multiplied it one way or the other, okay? They're meant to just give you a sense of what's going on, okay? But you may have failed the public test, the private test cases because your dot product didn't consider the fact that when you're multiplying matrices, they need to line up in the right axes, okay? Okay, so which is better, splitting weights or combining them together, okay? There's no right answer for this. For some purposes, it makes a lot of sense to split the weights, okay? Because what we do is we are trying to get the direction of where things are going, all right? To find the hyperplane, okay, to find the gradient, okay? And then we want an offset so that we can locate it in space in this hypercube in the appropriate intercept. Okay, so a lot of algorithms, especially connectionist ones, they deal with a separate bias term to cater for that. So when you separate them, the math comes out more cleanly. Okay, but many times it really doesn't matter because basically what we have is a set of weights, right? You can either say the weights go from index 0 to n, or you can say they go from 1 to n, and there's this separate term called a bias that's sitting out there. Okay, either way, the optimization works the same way. Okay, it's just that, again, for the bias, we don't actually observe it. Many times we just assume that the bias has an observation of 1. That means our x has this artificial x0 coordinate that's always set to 1 for every example. Okay. In midterms and such, will there be a lot of calculation questions? There will be some, okay? This is a math class that is disguised as a computer science class, or maybe it's a computer science class disguised as a math class. I don't know, okay? It's sort of in between. Machine learning is known by many different names. I mean, if you took it in the math department, it would be called curve fitting or function approximation. That is exactly what machine learning is. It's just that, it has a different name in the computer science department. Okay, so in statistics, you have to deal with approximation. In machine learning, we have to deal with learning. These are slightly different problems because of the fact that we are doing things in a different way. You have test examples that are coming in, and you don't have all of the data to work with. So it admits a slightly different characterization of the class, of the types of problems that we're going to talk about. Okay. In general, what are some common methods we can use for linear conversions other than using logs? Okay, there are lots. If you are able to take a more advanced class than what we can offer in this course, I highly encourage you. There are lots of really cool things in math, for example, kernel functions and radial basis functions. Those are ways to get an infinitely large dimensional space at very little cost through the elegance of mathematics. But unfortunately, we don't go through that much. Okay, many common things are very simple to think about. So things we can do are normalization, right? You did that before to center the data into a Gaussian sphere. We can sometimes square some of the attributes, right? So we can take x and x square it. Okay, that gives us a nonlinear exponential growth, so that things that have higher values are moved much farther away from the norm. You can do the opposite and scale it the opposite way, right? You can make big values smaller, and you usually do that through a log, right? So when you say logarithm, natural logarithm, or a base 10 logarithm, that usually compands these types of values, takes large values and takes them down a notch so that we can observe them closer to the origin. Okay. Other things that happen a lot are in the case of naive Bayes. So you already know in naive Bayes, right? We have this problem where or feature rather, that we try to make all of the features assumed to be independent of each other, right? So if you don't believe that the features are independent of each other, then you should be engineering features that are cross products, right? You can say, I'm going to take x1 and an x2, and I don't believe that they're separate from each other. So I'm going to introduce a new third feature. It's called x1 times x2. Okay, and you can see what that does, right? If x1 and x2 are highly correlated, x1, x2 would be really big, right? If x1 and x2 are inversely correlated, then this x1, x2 product will usually be very small. So this captures some intuition about capturing non-independence assumptions between features, okay? So those are some of the common things that we can do. But again, it really does help to look at your data to try to understand them wherever you're trying to get your data. Whether it's time series data, whether it's vision data, whether it's some type of form data or natural language data. All of these, you have to know a little bit about the domain. You can read a little bit if you're doing projects in those domains about how other people treat them, and then you can try to use a suitable nonlinear phi function, if you will, to engineer additional features that might make them easy to separate the instances. Okay. Okay, I think I've covered just about everything here, and it's already 5:53. So I'm going to let you all go. I think I've covered pretty much all of it. If you do have other ones that you want me to go through again, please do send me an email. I am unfortunately really busy, but I really like to talk to students, okay? This is why I hold these help sessions, okay? Because I want to interact with you, especially if you're struggling for whatever reason, you don't get the things that are going on in class, do contact all of our staff. Now you have 2 TA staff for your tutorials. You have myself, and hopefully this week you got introduced to your project TA and your backup project TA. So that's at least 5 people on our staff who were investing time to touch base with you, okay? So there's really no excuse for us not to, for you not to speak up in some form, okay? Because as we know, COVID is forcing everyone this way, but there are actually nice things about doing lecture this way. So I hope you engage us more, okay? With that, I'm going to stop here. I'm going to let you, tell me what else I need to do. You can annotate my slide if you'd like, or you can turn on your camera and say a brief hello if you don't mind talking to your lecturer. Okay, so I'm all good. If you have anything else, let me know.